This is 5.1.6 electromotive force and internal resistance. So these letters here, this is epsilon, Greek letter epsilon, and that's a lowercase r for internal resistance. So to start with, we have to think about batteries and what they are. So batteries are made of stuff. I'm not specifying what stuff, they're just made of stuff. And because they're made of stuff, because they have a physical form, they are some material, they also have resistance. Which might seem counterintuitive because you're thinking the thing that's generating the potential difference has a resistance. And the answer is yes, the thing that generates the potential difference also has a resistance. And we call that internal resistance. Now what I want you to do is I want you to imagine this battery connected in series with a resistor. But now you have the resistance of the battery in series with the resistor in the circuit. Now if we go back to potential dividers, we know that according to the resistances, the ratio of the resistances, the potential difference will split up amongst those resistors. So some of the voltage generated by the battery is lost inside the battery to itself. And the rest of it is then on our external resistor that we've connected to the circuit. So we call that lost volts, the potential difference lost inside the battery itself. But that basically means if we take the voltage of the resistor on the outside and we add that to the lost volts, then we have a total potential difference produced by the battery, and we call that the EMF of the battery, or the electromotive force of the battery, which is the total work done per unit charge. Let's build it up in terms of our notes. So, we draw a cell, we draw a small resistor, and we label that small resistor little r. We then draw a big resistor here, and we call this the load resistor. Now to help you imagine this, a battery in real life has the behavior of an ideal cell plus a small resistance. Now I'm going to sketch that on top of our diagram. So what I'm telling you is that if I drew this as a battery, yeah, and I've even drawn the little nib in the middle, because if you've got an AA battery, you've got the little nib on the positive side. So that's what a battery would have inside it. An ideal cell generating an EMF, so we'll label that as epsilon. A small resistance, little r, and a big resistance on the load. The equation linking these together is EMF is equal to the potential difference on the outside, otherwise we call this a terminal potential difference, V, plus the current, because it's a series, times by little r. Let's put a box around that. Now, we'll label these up. So that's the EMF, or electromotive force, measured in volts. V is the terminal potential difference, measured in volts. I is current, measured in amps. And R is internal resistance, measured in ohms. Now, I'll give you some more equations. If we take that potential difference, V, that's our terminal potential difference. So I would say V terminal equals to I times big R, and V lost is equal to I times little r. So all three of these equations can be used together simultaneously. And we'll define EMF as well and have that written down. So EMF is the work done per unit charge by the battery, which is the same as a joule per coulomb. So volt is the same as a joule per coulomb. Now, sometimes when you get problems involving EMF and internal resistance, the exam questions might provide you with a circuit diagram to begin working with. But they don't always label the internal resistance. So sometimes you will have to read the question and add that to the diagram yourself. So be aware of that and make sure, even if they haven't included it in the diagram, you might need to include it if you read the question carefully. And this is quite common. They do this quite commonly, where they won't label it in the diagram for you. Next, let's look at an experiment to find EMF and internal resistance. So we want to set up a simple circuit. So we have our cell, our internal resistance. And from now on, we just put a dotted line to show that it's a battery that has internal resistance, like so. We put an ammeter, a variable resistor as our load, and we put a voltmeter. So this load resistor, we can call that R. This is little r. This is EMF. So we're going to start by examining the theory behind this. So if I'm doing an experiment, we're not looking to make one single measurement and rearrange an equation and find what we're looking for. What we're trying to do is we're trying to make a relation between different quantities or different variables, and from that relationship we can make a graph, or we can plot a graph. That relationship will make itself obvious. So it might be a straight line, it might be a curve. We plot a line of best fit, and a line of best fit might be a straight line, it might be a curve. It doesn't have to be a straight line. It's not a line, it's not a straight line of best fit, it's a line of best fit, whatever that may be. And then from there we see if we can extract some data, usually in the form of what is the y-intercept, what does that represent? What is the gradient, what does that represent? So we look at the theory first. We start by writing the equation out. EMF is equal to V plus IR. Now from here, we can measure V because we've got a voltmeter across our load resistor. We can measure V. We can measure I because we have an ammeter, so we can measure V and I. We can measure V and I. Next, we want to rearrange this equation to make it in the form of something we can graph. So rearrange into the form of y equals to mx plus c. What that means is I want V or I to be by itself. In this case, V should be by itself because V is not multiplied by anything in that equation, whereas I is multiplied by something else. So we can keep V by itself. So I'm going to minus IR from EMF and have V by itself. So V equals to EMF minus IR. I can write things in any order I want. Yes? The order that I write this in doesn't matter. So let's change the order. Change the order to make it easier to see. So I'm going to write it as V equals to minus, I can put R first, R times I plus EMF. And underneath these, I'm going to write down what they mean. So you've got Y equals to MX plus C. That's our theory. We want to take measurements in order to obtain those results and make a graph, a straight line graph. So, next, the method. We measure V using voltmeter and I using ammeter. Very important skill here. Not just what you measure it with. Measure potential difference using voltmeter. Measure current using ammeter. Always say what you measure and what you measure with. It's not enough just to say what you've measured. Then we vary the variable resistor and repeat previous step until we obtain at least 7 sets. And take an average in order to improve the accuracy as well. But in this case, I'm not going to write that down. We record data into a table. Now, whilst we're saying record into a table, we should also show what that table looks like. So V measured in volts, I measured in amps, so you'll have some values recorded in here, whatever they may be. Next, we plot a graph. So when we plot our graph, we put V measured in volts on the y-axis, I measured in amps on the x-axis, and our results should look something like this. So you plot a straight line. Then we do our usual triangle. So you've got the delta x and the delta y. And I'll just write in here, draw line of best fit. The vertical intercept is EMF, and the gradient is minus the internal resistance because it's a negative value. To find the gradient, we draw triangle, and when we draw a triangle, our triangle should be at least 50% of the space available. In other words, make it as big as possible. If you make a small triangle, you don't get marks. It has to be as big as possible. The method is more important here. So draw a triangle at least 50% of available space. Use m equals to delta y over delta x to obtain value for gradient. Now a question could go on further, for example a 6-mark question that will ask you to also include some precautions that you take. Now when we talk about electricity and we talk about students often talk about getting electric shocked. The cell might be 1.5 volts. That's not going to electric shock you. You could hold it between your fingers, it's not going to electric shock you. The potential difference way too low. But what could happen is that the resistor could get hot. Now if the resistor gets hot, again using 1.5 volts, we're not going to have a resistor that melts or catches fire. It's not going to get that hot. But the precaution that you take is that you switch off the circuit or open the switch, and I haven't drawn a switch in my diagram, but you open the switch when you're not taking data, when you're not taking any measurements. Because the resistor could heat up, and if the resistor heats up, that could change its resistivity. Because conductors the conductors will increase their resistance when their temperature is high. So you want to prevent that from happening. Right, we'll talk about some typical batteries. Yeah? So, for example, you could have an alkaline AA or AAA battery. These typically have an EMF of about 1.6 volts. You could have a lithium-ion battery. These have a EMF typically of about 4.2 volts. and I'll put in brackets here, when we talk about these lithium-ion batteries, we're not talking about substitutes for AA batteries, because those lithium-ion batteries will have about 1.6 volts EMF as well. It'll be slightly less, actually. But when we're talking about these lithium-ion batteries, I'm talking about, for example, most modern devices, mobile phones, tablets, portable game consoles, anything really that is charged by a USB cable. Then we have the lead acid, which are car batteries. Lead acids usually have an EMF about 12 or 13 volts. And lead acid batteries also have very, very small internal resistance. And because it has a very small internal resistance, it can provide a large current during startup to the starter motor, allowing the starter motor to turn an engine. Because starter motors need extremely large currents. Now, internal resistances are usually quite small. And in order to get the most out of a battery, you want your load resistance to be much, much bigger than the internal resistance. Let's imagine something. So imagine the first diagram I drew. We've got battery with its internal resistance. We've got the load resistor. If my load resistor has the exact same resistance as the internal resistor, or the internal resistance, then you essentially have two resistors in series with the same resistance. The ratio between them will then be 1:1, which means that half of the potential difference is lost in the battery, and only half is what you get on the terminal. Now, if my internal resistance is 1 ohm, but my load resistor is 1 kilo ohm, the ratio is now 1,000 to 1. That 1 ohm internal resistance is now negligible. So if you divided up the EMF, 1,000 over 1,001 to the load resistance, and 1 over 1,001 to the internal resistance, you can see that it's a negligible loss volts. So you want your load to be much, much larger than the internal resistance. So what happens then if you short a battery? If you were to have a short circuit, that essentially means that you have created a low resistance path between one terminal battery to the other end of the battery. Now, if I said that the internal resistance is very, very, very small, and we've now short-circuited this battery, then according to V equals IR, all of the potential difference is now in the internal resistance. That means all the energy is converted into heat in the battery. You have large currents because V equals IR. So if you do V divided by a very small R, you get a large current. You've got large currents flowing through the battery. Battery is now transferring all of its own energy into itself through its internal resistance. So how does a battery transfer energy? Well, it heats up. because it can't do anything else. It can't create sound. It's not a speaker. It's not a motor. It can't move. So it doesn't really have any other useful function. So it heats up. And then you can get a battery that either pops or reduces its lifespan through heating. Yeah? So short circuit is a low, or I could write in brackets, approximately 0 resistance path back to the battery. According to V equals IR, with low resistance, because now the only resistance in the circuit equals to little r, you have large current, and battery heats up. Now thinking about that, in general, it's not a very good idea to carry batteries in your pocket with exposed terminals. Because if you have keys or coins in your pocket and they touch those terminals, then you effectively have created a short circuit of a battery in your pocket, which could get very, very hot in your pocket, which you want to avoid. So one safety precaution about batteries is don't carry them in your pocket. And that's the end of 5.1.6.